Perfect. Okay, so welcome everybody to a new IPARCOS seminar. Today it is a pleasure to introduce Laia Casamiquela, Dr. Laia Casamiquela, in this new seminar. Laia did her PhD in 2000, presented her PhD in 2017, and it was under the supervision of Professor Carme Jordi and in the University of Barcelona and Ricardo Carrera in the Instituto de Astrofísica de Canarias. And the PhD was about the chemodynamics of open clusters in the Milky Way disk, studying chemical gradients in the thin disk of the Milky Way, and this as part of the Ocaso survey. After completing his PhD, she moved to Bordeaux in the Laboratoire d'Astrophysique, sorry for my French, in Bordeaux. First with a postdoctoral researcher CNRS fellowship. This was for 2 years, 2018-2019, and after that, she got another postdoctoral fellow at the Centre National d'Estudes Spatials in Bordeaux also. This under the supervision or in collaboration with Caroline Subiran. After that, well, basically, she is now here in Bordeaux, and in very few weeks or months, she's moving to a new position, a new postdoctoral position in Paris, in where she will be working with Professor Misha Haywood and David Katz. She's also deeply involved in the Gaia collaboration. She's part of the CUA inside the Gaia collaboration, so working in many other of the groups of Gaia, and she was also very involved in Gaia during his PhD in Barcelona, and also is a very active member of several outreach activities that basically some of them together with the speaker in the last week, Ignasi Perez-Lafus, we are driving this outreach program here in Catalonia. So, well, apart from his very good research, he's also a very good speaker and also very good in outreach activities. So I'm probably missing many things. Like if you want to add something else about your career, please don't hesitate on doing it. And if not, you can start as soon as you wanna with the talk. Thank you for accepting the invitation, and let's go to the talk.
Okay, thank you, Santi. Thank you for the very extended introduction, and very nice also. And yeah, no, it's okay. I don't add anything else. You mentioned everything. Okay. So today I wanted to speak about strong chemical tagging and how because in fact this work has been done in collaboration with these other people from the Observatory of Leiden, from the University of Barcelona, and also from Caroline, which is my collaborator here in Bordeaux. And so we wanted to test the assumptions of strong chemical tagging, and we did it with known open clusters, and I want to explain you about this work. So first of all, I will start with a context, like very broad context for the maybe not so specialized audience. So first of all, the concept of galactic archaeology in general. So this concept has been out for a while. And let's say that it's like an analogy, traditional archaeologists study the human history by investigating the remnants that have been excavated and can be observed nowadays. Galactic archaeology want to trace the history and formation of the Milky Way galaxy using present-day observables of the stars, basically, and this includes their kinematics, ages, and detailed chemistry. Okay, so it has been known already for a while from observations and also from simulations that most of the stars form in gravitationally bound aggregates, and most of these aggregates tend to get dispersed in the galactic disk after some 100 million years from their formation. And so it is believed that those stars are the stars that then populate and increase the population of the galactic disk as time goes by. So then, for example, in the point of view of galactic archaeology, it would be very interesting to try to trace back those stars to their original formation sites and find the siblings of the stars. And this, in fact, would give an incredible wealth of information to unveil really the evolution and the formation of the Milky Way, but also the dynamical processes that happen inside clusters, the interactions with external structures like spiral arms, etc. Okay. But however, it is difficult to achieve this for structures like the disk in particular, because it is due to the fact that the stars and the gas in the disk are highly dissipated in comparison with other stellar structures, like the halo. And then, in fact, when you take a star from the disk, which is quite old, its dynamical information has been basically lost because it suffered dissipative processes. And you can really not trust so much classical traceback. Okay, so in fact, all of this problem hampers our understanding of the formation and evolution of the galactic disk. Of course, the story is completely different for the halo of the galaxy, where it is much easier to identify its building blocks from kinematics. And in particular, after Gaia DR2 and EDR3 also, a number of structures have been found in the halo through kinematics. Okay. So a particular perspective that was proposed in this review quite some time ago to overcome this problem is the concept of chemical tagging. So chemical tagging is based in the idea that stars that are born together and then quickly dispersed in the disk, as I explained, preserve in any case their birth chemical information in their atmosphere. So in fact, this happens for, let's say, low mass stars. For massive stars, the story is not like this, but for most low mass stars, when they form in these aggregates, they lock the chemical information from the interstellar medium, and basically now we can observe it. And the so-called strong chemical tagging holds in the assumption, of course, that all stars in our galaxy are born in form of clusters or aggregates from molecular clouds sharing the same chemistry. And under this idea, one should hope to be able to tag individual stars to their siblings. I think there's a huge echo. Okay, yeah, now, okay. So I was saying that under the assumptions of strong chemical tagging, one should hope to be able to tag individual stars to their siblings and their common parent molecular clouds in the end, using chemistry only, and then attempt to reconstruct all the birth clusters that once happened in the Milky Way. Okay, that would be very, very nice. However, there are two critical issues for this to work. The first one is to ask ourselves if conatal stars have indeed the same chemical signature. Of course, you need this because otherwise you won't be able to find siblings with chemistry. For this, there is some observational evidence for chemical homogeneity in open clusters, at least up to a 0.02, 0.03 dex level. And for example, I want to highlight this study, which I think was the first that really analyzed this. And they took solar analogues in the Hyades, and they found scatters, which are the black crosses for the different elements, which were in fact larger than their uncertainties in most of the cases, but indeed, so this allows to quantify the intrinsic scatter. Let's say they assume that they are seeing the intrinsic scatter of the Hyades cluster, and this is between 0.02 and 0.03 dex. And let's say that this is below the typical uncertainties when we are talking about, for example, large spectroscopic surveys like Apogee, Gaia ISO, and the futures for most width, etc. So typically they assume uncertainties of around 0.05. So in fact, for most of the studies, this intrinsic scatter is below the level of uncertainty. Okay. However, I already warned you that there can be large differences in chemical abundances in some elements inside the cluster, because during the life of a star, there are at play processes which change the surface abundances. And this is higher than this 0.05. For example, one of them is atomic diffusion, but it's true that it's localized mainly in the tarmac and subgiant stars. Also, there are some mixing processes from some elements in the red giant branch. And on top of this, there are several assumptions that affect our spectroscopic analysis that are very difficult to take into account, like some systematics and non-net effects, etc. I won't enter inside this, but these effects are really difficult to take into account. And for example, a mixture of all these two things can be seen, for example, in this study that we did last year, where we took stars of different spectral types or different temperatures. The color is the temperature, and the gravity is indicated by the size of the points. So we saw that inside the same cluster, we had stars in 3 different clusters. So inside the same cluster, when we were computing the abundances, we found very strong dependencies in spectral type, so in temperature, and sometimes which are funny and difficult to characterize. Okay, so of course, if you find this inside a cluster, then all the assumptions of chemical tagging start to be doubtful, because you need zero scatter basically to do some chemical tagging experiment. But in any case, this difficulties the analysis, all these effects. But let's say that there are some ways to overcome them. Okay, we will see that later. But now let's assume that in fact stars inside the cluster have the same chemical signature. Then there is still another question to answer, and the question is if the chemical signatures of the different birth clusters are different enough to be distinguished. Okay, this is not simple to prove. There were some studies that argued against it, some others that are more in favor, so it's quite debated. But so for example, these studies found that it was really difficult to identify co-natal groups of stars, because in fact, in the past giga years of the evolution of the disk of the Milky Way, there's a really large overlap in the chemistry of the interstellar nebula. Okay. So in this context, doing experiments in known aggregates like open clusters, so present-day clusters, stars that were born together and that really survived the dissipation, is really key, and they provide a laboratory for testing strong chemical tagging assumptions. Okay, and in fact, that is what we wanted to study. So what we did in this study was a selection of high probability members of clusters. So we took some nearby clusters, some membership catalogs that have emerged after Gaia, so they are based on really good astrometry and photometry. And so we queried for a huge amount of cluster members, the public archives. So we were looking for high signal to noise, optical, and high resolution spectra. And we queried these different instruments, HARP, SPHEROS, and UVES in the ESO archive, HARP North in the TNG archive, ESPADON, which is in Hawaii, Narval and LOD, which are in two observatories in France, and FIAS and Hermes, which are two instruments in La Palo. We also included in our sample the observations made in the context of Ocaso. And so within this large range of age and galactocentric radius of the clusters that we managed to get spectra for, here you have the XY plane and the Z RGC plane colored by age for all these clusters. We gather, in fact, more than 1,600 spectra corresponding to more than 300 stars in 47 clusters. Okay. We restricted ourselves to red clamp stars, and I'm going to explain why in the next slide, or I think it's in the other. Yeah. So now I'm going to go for the spectroscopic analysis. Okay. So to do the spectroscopic analysis of the spectra, we use the public tool called iSpec. And so I'm not going through a lot of details, but basically we run our pipeline which performs a spectral synthesis fitting in the spectra using the Marx model, the spectrum radiative transfer code, and the Gaia ISO line list, the last version of it. Also, since the data come from different instruments, we analyze, we did an homogenization of the spectra to be able to really compare the results and merge the results to a common wavelength range and to a common resolution. And we used a pipeline that is explained in detail in this paper. And basically, what we do is to compute first radial velocities. And this allows us to ensure the membership of the star inside the cluster, but also to pinpoints of some spectroscopic binaries, because those stars sometimes affect the chemical analysis. So in fact, we are interested in not having spectroscopic binaries in our sample. And then we compute atmospheric parameters and 1D local thermodynamic equilibrium individual line abundances. And for example, I can tell you that for the atmospheric parameters, this is the typical precision that we get. This is the median values, I think. And so moving forward, because, well, here I said that we obtain 1D LD individual line abundances, so abundances of each line for each element. And then we apply a special procedure, a particular technique, which is the strictly line-by-line differential abundance method. Okay. This is, I mean, it seems sometimes very complicated because it's a very long name, but it's not so much. I'm going to try to explain this. So basically, we use this procedure because like this, we can reach very high precision in the abundances. And most importantly, because it erases the differences that arise from some assumptions in the analysis. Those effects and systematic effects that I was telling before that affect our analysis. So this is one of the techniques to arise this type of systematic effects coming from, for example, wrong atomic parameters and unaccounted blends, etc. So basically, this type of analysis consists in using twin stars and take one of them as a reference, okay? And then compute the abundances line by line, subtracting the abundance of the reference, and then doing the mean. So basically what the formula says, okay? This is the abundance of one line of a particular element. This is the abundance of the same line of the same particular element in the reference star, and then you do the mean. Okay. So basically, the idea of all of this consists in using a reference star which is a twin of the other. In the case that we have solar twins or solar analogues, then of course the reference star is the sun, and then basically this differential value becomes the solar scaled bracket abundances that we are used to using. Okay, but in our case, in fact, we had red clamp stars, so helium core burning stars, nothing to do with the sun. And the strategy that we developed is to do our analysis with respect to one clamp giant in the Hyades cluster. Here you have it circled in red, maybe you don't see it, but in any case, the stars are not so different. And we chose one of the stars that was very, very well known, like the stars of the Hyades, and we did the differential analysis with respect of it. So in fact, primarily, we are getting how different this delta X, this differential abundance, we are getting how different all the other stars are with respect to the specific IPARCOS giant. But now we would like to transform it to meaningful bracket abundances with respect to the sun, right? So we assume two things here. We assume that all the IPARCOS stars have the same abundance, and we analyze a IPARCOS solar twin with respect to the sun differential. So this gets us a correction that we can add to the differential abundance, and then we obtain we can transform to get the solar scale abundances like this. Okay. So well, like this, as I said, we can really lower a bit this precision. So maybe not getting to the really 0.01 precision, only for the highest signal to noise cases. Okay, but let's say that in almost all our cases, the individual abundance values are, let's say, 0.03 dex. And internal precisions, for example, can be tested with the independent analysis of several spectra of the same star. So this happens. For example, here you have the same star, all the points are different spectra of the same star analyzed independently. And these are the abundances of different elements. These are the temperature and gravity obtained. And the scatter that these abundances give, in fact, give you an idea of the precision, of the internal precision. Of course, this was one of the highest signal to noise cases. Okay, so there were some cases where these scatters tended to be more 0.03, let's say. Okay, and so now we are interested, in fact, in the mean cluster abundance. So what we do is an average of the cluster stars. And you can see here, for example, how this looks like for the different elements that we can analyze, the 3 stars from the IPARCOS, and 5 stars for this cluster density 3532. And so, in fact, we saw that, our precision was quite good because we could have very low cluster dispersions, intra-cluster dispersions, okay? And of course, these dispersions are taken as uncertainties in the mean abundance value for the cluster. Okay, so now we would really like to know if we can really blindly tag stars to their siblings, given the low cluster dispersion that we obtain, which we highlight because it's quite high, this precision. So we restricted this part, in fact, to the clusters which had at least 4 members. Of course, because later I will explain that we perform a clustering algorithm, so we would like to have some members to cluster. Otherwise, you cannot cluster 1 member or 2. It's difficult. Okay. And also another important thing is that we took a subsample of abundances which have no missing values. This is because from all these abundances that I have shown here, in some cases, particularly, well, here all the stars have, here, for example, so this star did not have praseodymium value because we could not compute it or whatever. Sometimes it happens for a lot of stars inside the cluster. So in fact, we took the subsample of elements which had value for all the clusters. Okay. So the advantage of this experiment that we want to do is that it is a control sample, where we know really which star belongs to which cluster. And in fact, we have no field stars, no contaminations. So it is really the perfect scenario to evaluate the performance of clustering algorithms and what we can expect from them. The first thing that we did was to compare the chemical signatures of the cluster. So here we have all the clusters that we had analyzed, their chemical signatures in different colors. The different panels have increasing ages, and inside the same panel, the ages are also increasing with the color. So light is younger and dark is older. Okay. And the first thing that we saw is that in fact the cluster chemical abundances, the chemical signature, once we subtract the effect of the metallicity gradient, are really very similar. Okay. So this panel, the abundance is over Fe. So in fact, it would have been good to see some peculiarity for each of the lines, but we see that all of them follow like basically the same trend. Okay, so we conclude that the chemical signatures of the stars are quite similar, of the clusters in the end, no? And are very overlapping. So then we had decided to run a clustering algorithm in our sample, in any case, using the chemical abundances of the stars in this 16 dimension. And for this, we have chosen a density-based clustering algorithm, which is called HDV-SCAN. Okay, this is convenient in our case because so the most important is that it does not require an a priori number of clusters to find. Also, it can find clusters in arbitrary shape, and it can deal with stars which are not associated with a cluster, for example. And to explain the meaning, I will put this video. Hope it works. So, yeah, okay. So explain a little bit the algorithm. Basically, HDV-SCAN is the hierarchical version of the DV-SCAN algorithm, which is the one that shows the video. Okay. So DV-SCAN works by defining an epsilon neighborhood, which is the size, basically the radius of these circles that keep appearing, and it searches around each star for other stars within this neighborhood. And if a sufficient number of stars falls in the epsilon neighborhood, the group is considered a cluster. So there is this mean cluster size, which is a free parameter of DV-SCAN. Okay. So the main disadvantage that has DV-SCAN is that it is limited to a single density threshold, which usually corresponds to the densest cluster in the field. But on the contrary, the hierarchical version of the DV-SCAN method applies, in fact, the same run, the same algorithm, but at different epsilon possibilities. So in fact, we are able to find clusters with varying density. Okay, and in fact, what okay, so what it does is really to build a hierarchical tree, and it decides if each cluster, so the hierarchical tree in fact represents a different epsilon taken, and it decides if the clusters found at the bottom of the tree are really a cluster or not, depending on what is called persistency, which is like the resistance of the group to be divided once we lower and lower this epsilon. Okay, and for example, this is seen in this simple example, like this 1D distribution of points. So here, the hierarchical DV-SCAN would make this tree. And what it's seen is that, in fact, the persistency, which let's say it's like the area, the surface in these things, of these two together is larger than when the cluster was considered one. Like when we consider this a cluster, the persistency is lower than when we consider these two separately. This is the opposite if the valley inside these two peaks is higher, because then the persistency here is much larger. So you keep lowering the epsilon, and this is still considered a cluster. And it is just when the epsilon is very small that the stars are divided into two. So this is how HDV-SCAN finds the clusters and decides which are clusters and which are not. Okay. So the main free parameter of HDV-SCAN is the minimum cluster size. Okay, this is a quite intuitive parameter. Fixes the minimum number of members in each group that are going to be considered a real group. And we chose it to fix it to 2 because in our case, so since we have the clusters with fewest members have 4 stars, this would allow to recover at least one cluster at 50% completeness, let's say. Okay, so we found this reasonable. However, the performance of the algorithm, in fact, further depends in 2 other parameters that from HDV-SCAN that control how conservative the cluster is. So these ones are the minimum samples, which is not very intuitive, but in the end, a low value of minimum samples makes the algorithm sensitive to more local density fluctuations, while a higher value captures more global pictures, like more global clusters, okay? And the other is the cluster selection epsilon. And this is in fact the minimum epsilon to be considered. So it ensures that the clusters below a certain given density are not split any further, okay? So these two parameters, in fact, we saw that in the end, they affect quite a lot the results of the clustering, even if they have some default values in the implementation that we use. But the optimal values really depend on the data set that you are using. So again, we have the advantage that we have a control sample and we can evaluate their effect really easily. So what we did is compute different diagnostics, sampling different combinations of these two parameters. And here we did this sample, and we were able to choose the more adapted values. Here are all the different parameters that we considered. Okay, I want to highlight these two panels here, which are the recovery fraction, because they are the most intuitive ones. And so the recovery fraction is basically the fraction of successfully recovered groups with respect to the initial number of clusters. But of course, how do you define this? Well, we consider a cluster is successfully recovered when the group it is assigned to exceeds a given homogeneity and completeness thresholds. Okay, I'm going for this, but the two thresholds were 40% and 70%. So homogeneity means that the group contains only stars from a single cluster. So if a group is 100% homogeneous, means that all of these stars that are assigned to were in fact stars from one given cluster. And completeness means that all data points of a given cluster are in fact members of the group. Okay. In fact, we would like both of these indicators to be at 100%, but of course this never happens. And we defined two thresholds: 40% threshold in homogeneity and completeness, and 70% threshold in homogeneity and completeness. Okay, and this is the results that we got in a heat map. And in fact, what we saw is that the highest values, so the highest values of these indicators happen at low epsilon and at low mean samples. So we decided to take mean samples equal 1 and epsilon equal 0.05. Why? Well, the two 0.05 and 0.01 gives the same, but so this epsilon is somehow related to the level of uncertainties that you have. So we decided that 0.05 was more more theoretically adapted to our case. Okay. So we ran the algorithm, and to better visualize the groups found in the chemical space, we use the algorithm UMAP. Okay, this algorithm performs a reduction of the dimensionality of our chemical space because we have 16 dimensions. And it reduces to 2. The advantage is that it provides, so it preserves the global structure of the data. So it's very good to visualize the results of a clustering method, in particular in our case. So I show here the two projections of the UMAP for all the stars in our sample. And the original clusters are colored here. Okay, so this is the positions in the UMAP colored by the clusters where they belong to. And the groups found by HDV scan in the best configuration scenario are colored here. The gray points are considered noise. Okay. So in fact, we see already that in the right panel, the central part of the distribution has a super large mixture of stars of different clusters, which are really confused. In fact, by eye, it would be extremely difficult to distinguish any cluster. Only some structures can already be identified as clumps in this space. For example, this here, which belongs to the cluster NGC 6705. or this here, which is like the most metal poor clusters that we have in our sample. And these are the ones that are basically recovered. Okay, so for example, persistently we recover NGC2420, which is one of the most metal poor clusters known, and NGC6705 because it has the particularity that it has a high, so an alpha enhancement. Okay, then some other clusters are considered recovered under the 40% threshold in the completeness and homogeneity. This is 9 clusters, so it represents 29% of the sample. However, if we higher this threshold in homogeneity and we require that at least the groups that are considered recovered had 70% homogeneity and completeness, then only 1 cluster is recovered. Okay. Then we did some further tests. And because we realized that some clusters that were successfully recovered are also those that have larger number of stars. Okay, and we wanted to see if this really had an effect. So what we did is take the clusters which at least 6 members, and this restricted our sample to, I don't remember the number, but maybe half of the sample, maybe it was 10 or 12 clusters. But all of them had more than 6 members, okay? 6 members or more. And we didn't see, in fact, that the recovery fractions really increased. So this is to be compared with the 29 before, and the 7% is to be compared with the 3%. But here the total sample is lower. So in the end, it doesn't represent a huge increase. Then we also investigated the possibility of finding known clusters in a large data set for really a blind strong chemical tagging experiment with field stars. And we used the Apogee Red Clam catalog, which is one of the most adequate catalogs for our purpose because it contains a large number of stars with good quality abundances in a very small bin in the HR diagram. So it mimics kind of the differential thing that we were doing. And so the systematic abundance trends are minimized, not exactly erased, but minimized. And we have to take into account that, in fact, apogee abundances have larger errors involved than the sample we had before. But indeed, we wanted to test how the algorithm worked with this, with the inclusion of noise, okay? So in this catalog, we only could find 4 known clusters with a minimum number of 4 stars. These are colored in here. So these are the UMAP projections, again, of the apogee sample, the Red Clam apogee sample. And what we immediately saw is that the maps present clear patterns. So for example, here we see a very large structure, which in fact is identified with a thick disk. But there are other clumps that in fact are not really identified. And most importantly, the clusters, the stars from the clusters are really dispersed. I mean, yeah, they are compatible. Probably they have compatible abundances, but in the end, they are dispersed, more dispersed than we would like to be grouped. So when we ran HDV scan, we also did the same sampling of the different I don't know how to say it now, the different possibilities of the free parameters of HDV scan. So we could find the best case. And in the best case, we ran HDV scan and we find more than 200 groups identified. But in the end, none of them contains stars from the clusters. In fact, I think we recovered these 2 stars in the same cluster, but mixed with other stars. Okay, so in the end, we had a very poor recovery. Great. So on the other side, another test that we wanted to do is that it is not clear whether using several chemical elements that are representative of the same nucleosynthetic path improves or worsens the results. So we tried to test whether the restriction of some significant sets of elements, particularly for the apogee sample, could improve the results. And in fact, it was not the case. I have not put the results here, but we tested with these two sets of elements, which are studied by these two studies here and are recommended for them. And the recovery was very similar to this 10% or even worse. I mean, I don't want to really judge this because it's really difficult to judge a performance of a 3 sets of abundances that they give very poor recovery in the results in the end, in the results of the HCV scan. Okay. And so after this, I have reached my summary and conclusions. So basically, I have shown you how we can test the strong chemical tagging blindly using high precision abundances of known open clusters. We analyze chemical signatures of more than 30 known clusters with red clump stars, and already we see a very large overlap. The applying of a HDV scans or machine learning algorithm is only able to distinguish some of the clusters. And in fact, 70% of the groups that are found are not real clusters. We show that the recovery of known clusters in the apogee red clump sample seems a less favorable case. And in fact, I wanted to highlight that this contrasts with some of the findings, for example, this paper that came out last year, where they used strong chemical tagging with apogee, and they found 21 candidate star clusters that they consider can be real siblings of birth clusters. Okay, and this is one of the plots that they show where the groups found, which are in orange, this is the dispersion found inside the group, the dispersion in abundances. So they highlight that in some of the cases, most of the cases, I would say, the dispersion found for these groups, the chemical dispersion, is lower than the real clusters, the real known clusters in apogee. Okay. So there are some still controversies in the literature. So our conclusion, in fact, is that blind chemical clustering in chemistry only in large group of stars, so using large spectroscopic service results, are difficult to interpret, given the caveats that I have shown. So in fact, we wanted to give a word of caution for strong chemical tagging perspectives, because it's true that when we look for clusters, it is really probable to find clusters. But then we need to understand if those clusters have chances to be real or not. Okay. However, it is true also that we can learn something also from this experiment. And it is that, in fact, across the age of all the clusters that we have analyzed, which are several gigayears, we can probably conclude that the interstellar medium has been very well mixed, because the clusters were formed in different places, probably. And this is also shown by the gradient of the abundances. But in the end, when we compare the real chemical signatures, we see that they are the same. So in fact, there has not been any peculiarity in the chemical peculiarity in the interstellar medium over the past gigayears. And finally, I also want to say that I was talking all the time about strong chemical tagging. There exists also, I have not explained this, but the weak chemical tagging, so the weak acception of the chemical tagging technique has been widely used in the literature. And in fact, it is used to find stars that were born in similar galactic environment and that show similar chemical patterns. And for example, this is the case of the identification of large structures, like for example, the thick disk, or also more particular structures, like for example, this nitrogen-rich population that was found by this paper. But in contrast, I have explored the idea of really finding stars that were born in the same star formation event, which is the same birth cluster. Okay. And to finish, I will just put the paper, the propaganda bit of the paper that was recently accepted. And I will finish here, and I can take some questions if there are some. Thank you for your attention.
Thank you a lot, Laia, for this very nice talk and also very illustrative of this problem of the chemical tagging. And now we will go to the questions session. Please, the people in the audience, you can just turn on your microphone and ask your question, or if you don't know how to do it, you can raise your hand or just ask the question through the chat, and I will read it for you. So if somebody has a question, please just turn on your microphone. Okay, David Montes has a question. Please, David, just proceed with your question.
Okay, hi, Laia, thanks for this very interesting talk. I have many questions, but because it's very interesting and we also working on that and sometimes in a different way. But for example, for the homogeneity inside the cluster that you mentioned, you show some plots that see some difference depending on the spectral type, no?
Yeah.
And I think that this difference in probably coming from the, for example, where there are more differences are just in the hot stars that are more difficult to derive abundance, for example.
Yeah, of course, if you go to very hot stars, it is very difficult, but indeed here, the stars are not so hot. So we were restricting to really FGK stars here. So the maximum is, well, a bit up of 60 to 100, let's say, Kelvin.
Yeah, I see.
And here, also in this part, there is a huge dependence. So you see this real trend, even if we consider stars from 5,900 to 500 to 5,000 Kelvin. So really in the G range of spectral types, you see this. But honestly, this is not only the diffusion. I mean, the diffusion, for example, only affects hot stars, as you are saying, but well, turn-off stars. But I think that all the spectroscopic analysis have these dependencies because the typical assumptions, you know, LTE, 3D, etc., that really put some systematics in here, or the treatment of the blends, you know, and also between main sequence and giants, we also saw huge differences. I mean, I don't have other elements show also very large offsets, I have to say.
Yeah, I see. You are restricted to this range that is not so much.
Exactly.
I think that you are more hot star when I see the plot very rapidly, but now it's not just the temperature is different, as you mentioned. Yeah.
Exactly. There are some things that can be attributed to other things. For example, in Ruprecht 147, there is this star, which in fact it's up in the AGB. So there are other difficulties because it's much colder and it starts to be supergiant, you know, and then this star gives a lot of problems. But even if you restrict to the good range of FGK normal stars, the best stars to derive abundances, you can find large differences. Also, this has been seen, I think, in other studies. I have cited mine, but there are studies in Gaia ISO also that do this.
And why you restrict to these red clans giants?
Here, yeah, because I can, because you can reach farther away in distance. Yeah, that is the main reason. Yeah, for the closest clusters, of course, I could do this with dwarfs, with solar twins, basically. But you cannot go farther away.
Yeah. And for the cluster that you use, you say that use your method to analyze the membership, taking into account the radial velocity and also Gaia proper motions and
So in fact, when we as a starting point, we took a external membership list, okay, the ones from Cantagodan. All based on Gaia astrometry. And then, of course, there are some probability cuts that you need to do. But also, since we get one more dimension, which is the radial velocity, sometimes we realize that some of the stars that were considered members in Cantat Godin, and that maybe don't have the highest probabilities, but we were keeping them because we considered them members. Then once we get the radial velocity is very different from the mean radial velocity of the cluster. So then we can constrain better the membership using this. That's what we did. Mm-hmm.
But you use also arc diagrams or color magnitude diagrams to analyze the membership?
Yeah, well, yeah, for sure. We check them, but in fact, if of course the general membership lists like the one in Cantat Godin are super good because they are homogeneous. But then when you go to a particular cluster, you can like really try to define a little bit more the probability threshold that you take. So in order to take less contaminants, but in the end, if you have, if the star is compatible with being member of the cluster from parallax, from proper motion Radec, and radial velocity, if it is a bit away in the HR diagram, you don't, in my opinion, you don't have strong reasons to reject it as a member because it can have some companion clause, it can be some problems in the photometry, for example. So, in fact, the membership constraint, we use it from this, from the Gaia membership list plus radial velocity that we are getting. Yeah.
Okay, and you use a differential abundance method. You explain this comparison with a rep giant more similar to your star, no? And then transfer this to the sum, but this is just for have an homogeneous values, no? Because if you are interested just in one cluster, it's better just only do the star of the cluster, no?
So of course, well, I'm not sure I understand 100% your question, but of course we could do the same analysis without this transformation. Okay, we could do the same because in fact we have a differential abundance with respect to the IRS. Okay, but it's a 0 point in the end. But since I mean, we think that it's better to stick to a common reference value, and we found this way of using the analysis of IRS solar twin with respect to the sun in the same way, so without losing the precision, etc. We thought that this was the best way to present the abundances in the end. But of course, there's only a 0 point between the differential values and the bracket abundances. Yeah.
And you say that using twin stars and take some of them, but this is because you don't have a sound spectra in this case, or what? Yeah,
you mean this? When
you mentioned that use the twins solar stars.
Here, no, I use the solar twins in the Hyades. I analyze them with respect to the sun, and that's why we have this correction. In fact, so this correction from the value of the Hyades differential abundance with respect to the sun.
Twins star inside the Hyades cluster.
Exactly. Since we, of course, we are assuming that the Hyades have the same abundances, that the Hyades giants and the Hyades dwarfs have the same abundances. But
then, twin star, what you call twin star? Not solar twins. Twins to the cluster.
No, solar twins. So you take the Hyades cluster, and in fact, we had a lot of stars in the Hyades. We take the giants, and we do the analysis of all the other clusters with respect to the giants in the Hyades. And then we take the solar twins in the Hyades. So there are some stars that have the same temperature of the sun in the Hyades. And analyze them.
But not the same abundance.
Almost 0.1.
But not different with the respect to the sun.
But it's not so different. The Hyades has 0.1 dex. Abundance.
Depends on what you want to do.
That's right. But okay, maybe not twins, but they are analogues in the end. So I think there are some confusion in the literature with the two terms. So I think solar twins, maybe it's more restricted. but let's say analogues. So there are a lot of stars at 5800K and 4.4 in log G. But it's true that the IRS has an abundance of a metallicity of 0.12, and in the end, the solar twins are restricted to less than 0.1. So it's true that we go a bit further, but we consider that the analysis holds because of the precision that we are getting in the end.
Yeah.
Mm-hmm. Yeah. I should call them solar analogues. Yeah.
Yeah, I understand. And the cluster that you use, at some point you say that difference in chemical is not so much. So you are covering a range of metallicities very different from one to others, or
this all the class. So this is the
abundance in, but just the iron is
here, is in this column.
Okay.
So, well, in fact, they have different metallicities. Yeah. So this must be 0.15 or 0.2, and it goes down to minus 0.25. I mean, well, you cannot go much different if you take open clusters, in fact. But so yeah, I mean, you can see that they have different metallicities. But once you remove the overall 0 point, the chemical. So the trick here is the chemical symmetry is so overlapping.
Mm-hmm. And when you do the analysis of the clustering, you are using the individual determination of abundance for each cluster.
For each star.
Yeah.
For each star. So here.
But each point is one star.
Exactly. For example, this point, each point is one star. And all these points, well, here you see it better. So all the points that are colored in the same way mean that they are one single cluster. So these stars come from the same cluster. These no. This one is from this cluster, apparently, but it's a bit different. Or these ones, which are green, are from NGC 2420. So yeah, it's individual stars.
Yeah, I understand. And later you compare with Apogee, but for Apogee you use the abundance that's coming from the Apogee pipeline, I suppose.
No, I use the astro-NN catalog.
And this is another determination of
it's a value-added catalog, I think so. It's inside Apogee data release.
Yeah.
So in fact, I wanted to use it because I wanted to mimic the study that I mentioned here, where they also use the astro-NN abundances. So in fact, I wanted to be like in the same, taking the same sample as them.
But in any case, these abundances are not differential as you do.
No, for sure not. No.
And this can be, in this case, different results because they are not differential, no?
Exactly. So yeah, you expect worse precisions. Yeah, that's for sure.
The final, why do you think this difference between your results and the one for this paper that say that recover more than you?
Well, that I don't know. It is true that they perform the clustering in a different way. So they use a DB scan. So they use a very similar algorithm as me, okay? But it's true that they difficult to explain. So they take the abundances as a function of stellar mass. So if I'm not wrong, or temperature. I don't know exactly. I think it's of stellar mass. And so they do the clustering differently. Not really. Yeah, they really in the abundances, but they consider that the abundances are a function of stellar mass. And somehow they are able to integrate this in the clustering. And they claim that like this, they can erase the systematic effects, which are everywhere also for Apogee. These systematic effects in the abundances with respect to spectral type. And so they have more stars. They don't use only red clump stars. And yeah, and then they claim that they find these 21 candidate clusters. Yeah,
this could be a good point that there are more stars, not only the red clan.
Yeah, this could be a good point also. Yeah, it could be that I am missing them. But it is true that in their paper they try to use the same algorithm to find the known clusters in apogee, and they don't find them. So they find some groups, but they don't correspond to the OCAM sample of apogee clusters.
Yeah.
So for me, that is a bit I don't know how to see it. It's a bit inconsistent. So I don't know how to solve it.
Yeah. In any case, you see that a strong chemical tagging is difficult.
At least difficult, because I guess that I mean you can do better maybe using another algorithm. I'm sure.
So but, I always think that it's better to the weak chemical tagging. So
exactly.
using additional information, kinematic, all the ACE indicators. In this way, you combine different things and can give more results. Yeah.
Also, I think that maybe a strong chemical tagging, well, maybe no, it is like this. Strong chemical tagging can be used, for example, for much older structures like globular cluster-like streams and so on, which really have very different chemical
signatures. Exactly, yes.
And so really you can identify those old structures. But let's say in the latest 8 gigayears of the disk, is what I say, that from this I learned that the ISM was very well mixed, and really the clusters are not different.
The chemical is very different and not so small difference as we are interested in. Yes.
Exactly. Yeah.
Okay, good. Very
Thank
nice.
you for the questions.
Perfect. So thank you, David. We have a few minutes for some question in the audience, and if not, we can leave it here. Very interesting talk, Laia, and very interesting discussion. This one-by-one discussion with David. So very
for
good,
sure.
Seminar today. And well, thank you all for accepting the invitation. Thank you a lot for the talk. And I invite all the audience to come again to the IPARCOS seminar. The next one will be not next week, but in 2 weeks, the November 5th, on Friday also. And it will be by Miguel Ángel Sánchez Conde from the Universidad Autónoma de Madrid. So you are all invited to come to the next IPARCOS seminar in 2 weeks. Again, thank you, Laia. Thank you to the audience.
Thank you.
And
thank you for inviting me.
Thanks. Bye-bye.
Bye-bye.
Okay.
Thanks.